All right. Well, happy Friday, and hope you guys are doing well. Today, I want to talk about some descriptive statistics. So we've been doing a lot of kind of data visualization, and data visualization is great, and it's an excellent tool. In addition to data visualization, as far as understanding and learning about our data, it's helpful to use what we would say are numeric summaries that describe our data. And so that's what we're going to take a look at today. Okay, just code. We're going to load up the tidyverse. Okay, so we've got summary statistics, okay? And these are numeric values that we can use to describe and summarize, some aspect of a distribution. Okay. And so, some of these things, probably you're familiar with a lot of these things already. So I imagine you're already familiar with the mean and the median. Okay. Probably already familiar with the range. But maybe not interquartile range. Maybe, I don't know. Standard deviation and variance. Maybe you're familiar, maybe not. We'll talk about all of these things, okay? And these are useful as far as just describing the values that we have in our distribution. So, when we talk about the distribution, what we're basically thinking about is like in a data set, think of like one of the columns, okay? So later on, we'll take a look at the penguins data set, and one of the columns is the body mass, okay? So just think about all of the numbers in that column, which is basically the weight of the different penguins. Some penguins are bigger and some penguins are smaller, and so you have penguins with different body masses. And, I think there's, I don't know, like 1,000 penguins in there, right? Or maybe not 1,000, but a few hundred penguins in there. And we just want to be able to describe kind of the overall kind of the distribution of all of these numbers without necessarily having to talk about each individual penguin, every single one, okay? So let's talk about the mean and the median. Okay, so the mean, you add up your numbers, you divide by how many you have. So sum of values divided by number of values, okay? And what the mean does is it balances the deviations. So I've got a few diagrams showing this, but basically you'll have positive deviations from the mean and negative deviations from the mean, and those things add up or cancel each other out, okay? The mean is sensitive to outliers and skews. So if you have an outlier or extreme value, the mean gets pulled in the direction of those extreme values, okay? And so, if you take the largest value and you increase it, the mean is also going to increase, right? And the way we calculate the mean in R is we just use mean, and then we give it the vector x. The median is the middle value, which basically means half of the data is at or below the median, and half of the data is going to be at or above the median, okay? And so what the median does is it balances the counts. The number of values above the median is equal to the number of values below the median. So these both of these things, you got the mean, which balances the deviations. It also kind of like, if you had like a scale, it would like be the balance point. And then the median kind of evens out the number above and number below, okay? The median is what we would say, in contrast to the mean, is robust to outliers, okay? So if you take your largest value and you increase it, the median is going to be unaffected, okay? And then we find the median in R by typing in median, okay? In a perfectly symmetric distribution, the mean is equal to the median, but in cases where you have something skewed, the mean is going to get pulled into the direction of the skew, okay? All right, so I've got just kind of a diagram here, right? So my numbers are 1, 2, 3, 4, 5, 6. And I put little dots here at 1, 2, 3, 4, 5, 6 along the number line. This red line here represents the mean, okay? And you can see each of these arrows would be one of our deviations, okay? So the 0.1 is 2.5 below the mean of 3.5, okay? So our mean is 3.5, and 1 is 2.5 below that, so it's negative 2.5, okay? 2 is 1.5 below 3.5, and 3 is 0.5 below, okay? 4 is 0.5 above, 5 is 1.5 above, and 6 is 2.5 above. And so you can see the negative deviations on the left-hand side exactly cancel out the positive deviations on the right-hand side, okay? The median is going to be the spot where half of the points are above and half the points are below. So if I ask what's the median of x, I get 3.5 there, okay? So in this case, our distribution is perfectly symmetric, okay? And so the mean and the median are both equal to 3.5, okay? All right, here, my last number, I replaced 6, I increased it to 9, okay? So what happens? My mean is now 4. 1 plus 2 plus 3 plus 4 plus 5 is 15 plus 9 is 24. 24 divided by 6 is 4, okay? So my mean is 4. And so we think about our negative deviations. So 1 is 3 below 4, 2 is 2 below 4, and 3 is 1 below 4. So my negative deviations add up to negative 6, okay? I have no deviation at 4. 4 is at the mean itself, so there's no deviation, so it gets a 0 there, okay? But 5 is 1 above, and 9 is 5 above 4, okay? So over here, these numbers add up to negative 6. These add up to positive 6, so the mean balances the deviations, okay? Median, still going to be 3.5, okay? Here, I can just kind of keep making it more and more extreme. So I got 1, 2, 3, 4, 5, and 27. I think that adds up to 42. 42 divided by 6 is 7, okay? And so here my mean is 7, and all 5 of these numbers down here are below 7, and I've got deviations of minus 6, minus 5, minus 4, minus 3, and minus 2. That adds up to 20, okay? Negative 20. And then over here, 27 is 20 units above 7. And so the negative side cancels out with the positive side. We get, 0 there, okay? Median is still going to be 3.5, okay? And then just to take it even more extreme, I've just pushed this one out even farther, out to 57, okay? My mean is now 12, and my deviations over on the left-hand side are minus 7, minus 8, minus 9, minus 10, minus 11, and that adds up to negative 45. And then over here, we have a deviation of 57 is 45 above positive 12. So anyway, that's what the mean does. It balances out the deviations below and the deviations above, okay? And then the median in all of these things, even though this number out here gets more and more extreme, the median remains unaffected through all of that. Okay, let me give you your first view quiz answer today, which is the letter D. D as in dog. Okay, so silly, just a couple silly examples here. All right, so if we're talking about something like income, okay, income is a distribution that is very skewed. And so, just imagine you have a room, a restaurant where people are meeting, and then there's 6 people in there and they each make $60,000, okay? What's our mean? Our mean is going to be 60,000, and then our median is going to be 60,000, okay? Now let's say a billionaire walks in, okay? All right, and so now you have 7 values in there. You have 6 people making 60,000, 1 person making $1 billion, okay? What's the median? The median is going to be the middle value, I guess not still the 4th value, but it's the middle value of 60,000. That's unchanged. Okay, but what's the mean? The mean is now you've got 360,000 divided by 7, and so your mean is going to be like $143 million. Okay, probably not reflective of what we would consider to be the typical income in that room. Okay, the mean is dragged upward, pulled upward by the extreme value. Okay, and then so because of that, you might wonder, like, well, why don't we just use the median all the time? Okay, well, sometimes you do want to take into account the extreme values, and that is important. And so, for example, let's say you have like a auto insurance company, all right? And let's say you have 100 customers, okay? Most of the time, all right, as an auto insurance company, your ideal customer is the customer who doesn't get into any car accidents, okay? Because you're just collecting money from them, you pay nothing out, you get to keep everything, okay? But the deal with the insurance company is that if somebody does get into an accident, the insurance company steps in and says, okay, we'll pay this out, okay? All right, so imagine there's 100 people, like 100 customers for this tiny little insurance company, okay? And most of those people, no accidents, $0 in claims. Some of them have small accidents, maybe $1,000, and then one person has, a serious accident where they have to pay out $50,000, okay? The total that had to get paid out, if you add this up, 50,000 and then 1,000 is 59,000, okay? However, what is the median payout? The median payout is $0, okay? And so if you're the insurance company, you're saying like, okay, well, how much should we charge for a premium, okay? How much should we collect from each of our customers, okay? If you go off of the median, 0, okay, well, you're going to be in trouble, okay? So in order to kind of break even and just kind of cover your bases, right, for the 100 drivers, you need to charge around $590 per customer here, okay? And then basically these 90 people who've been paying $590, and so all of their money goes to pay the, kind of the big accident at the end. But that's how that works, okay? So kind of like insurance things where you do like you want to make sure you are covered for kind of these extreme values. That's where the mean comes in, okay? So different cases, different examples. The mean has nice statistical properties, and so we actually like to use the mean a lot. But there are cases where, yeah, you know what? Maybe the median makes more sense to use to kind of describe our thing. Okay, another important aspect that we want to talk about and describe when we're describing our data is spread, okay? Spread is kind of the idea of how similar our values are to each other or how different the values are from each other, okay? So just some examples. If you imagine visiting an elementary school, okay? You go to the second grade classroom and you ask, how old are you, right? You ask each student in the second grade classroom, how old are you? And you record this information about ages. Pretty much all of the kids in the second grade classroom, at least in the United States, are going to be like 7 years old or 8 years old, okay? And so as far as what is the spread in ages, you have very little spread in ages because all of the values are very similar to each other, okay? All right, you go to a college classroom and you ask, okay, how old is everybody in the college classroom? Now you're going to get a little bit more spread, okay? Most of the people are going to probably be, late teens, early 20s, okay? 18 to 22 is probably most common, but you're going to have people who are older, 25, 29, things like that, where, maybe they had a career or they, are coming back or something, military service and going back to undergrad, all right? And so you're going to have more spread there, okay? It's not like, in the second grade classroom, everyone's going to be like born in the same year, right? Okay? Or in the college classroom, now it's like, when did you graduate high school? And it's going to be a little bit different, okay? And then you imagine going to the DMV waiting room or a doctor's office or someplace like that, okay? And now you're going to have a large spread of ages, okay? Because you're going to have teens, you'll have adults, you'll have seniors, you'll have young children of the adults and things like that. And so you have a large spread. And so instead of just using vague terms like there's a little bit of spread here or a lot of spread over there, we can use numeric values to quantify it, okay? And so the numeric values that quantify the amount of spread, we have variance and standard deviation along with interquartile range, or the IQR, and then range, I don't have any slides dedicated to range because I'm assuming you guys already know range, right? Max minus the min, that's range, okay? And then obviously range is going to be affected by extreme values. So, you know, where you have 57, you're going to have a big range, you know, even though you're just changing one extreme value there. Okay. All right, variance and standard deviation. How does this work? Okay. Standard deviation is just the square root of the variance. The variance, we can think of this as the average squared distance from the mean. Okay. The symbol that we use for the variance is s squared. And the way we calculate it is we do x minus x bar, each x, all right? So this is, maybe I should put a little subscript here, but basically each x in your data set, you're going to subtract off the mean. Symbol for the mean is x bar. You're going to square it, take that difference, and you're going to square it. You'll add it up for all the values in your data set, and then you're going to divide by n minus 1, okay? So the numerator is like the square distances, and we're adding them up. And one thing is like to calculate the averages, you divide by how many you have. And when we're doing the variance, we divide by n minus 1 instead of n. This is how we calculate the sample variance. The reason behind this is called Bessel's correction. It's a little bit beyond the scope of this course. If you are going to like major or minor in stats, data science, or data theory, you'll take a mathematical statistics course later, 100B, and you'll get into why we're dividing by n minus 1 rather than n. But it comes from the fact that we don't actually know the true mean of all of the values, but we only know the mean of the data we've collected, which is not necessarily going to be equal to the true mean of all of the values. But anyway, we calculate the variance in R by typing in var of our vector x. Our vector x has our values, okay? And then the standard deviation is the square root of that, and that's just found by doing SD, okay? So you just take whatever this is, throw it inside the square root, okay? And you might wonder, like, why are we bothering taking the square here and then taking the square root, okay? So, because, all right, so here's kind of the diagram here. So remember we had this data set 1, 2, 3, 4, 5, and 9, all right? And so here's my mean, and basically what I'm doing is I'm taking the deviations, right? How far each dot is away from the mean. And I'm kind of saying like, hey, what's the average deviation? What's the average, like, are the arrows on average really long or are the arrows on average short, okay? Because if the arrows on average are really short, right? Like if all of the kids are the same age, basically I'm gonna have just a whole bunch of short arrows here, okay? And so if the arrows are all really short, we have a small standard deviation. If all the arrows are really long, we've got a large standard deviation, okay? And so you might like, well, why not just take the average of the lengths here, okay? Well, one is if you have positive and negatives, they'll cancel each other out. So you might say, well, why not use absolute values, okay? And you can actually use absolute values. There is another measure of spread called the mean absolute deviation, and that's just like taking the length of the arrows, the absolute values of them, and taking the average, okay? But it's actually less preferred because the standard deviation has some nice properties. One of the big drawbacks of using absolute value is, like, in calculus, you learn that the derivative of the absolute value function doesn't exist at 0, right? There's that little right corner there at the bottom, and so that like breaks some stuff, okay? And then there's also like not always a unique solution to what minimizes some of these things. So anyway, we use the standard deviation. We use this, we square everything, and then we take the square root, okay? Squaring everything makes everything positive. We take the average of those, and we take the square root, okay? And then, yeah, the square function is nice, is smooth everywhere. We can take deviation. So anyway, if this is our data set, 1, 2, 3, 4, 5, 9, my mean is 4. I've got my deviations, okay? -3, -2, -1. 0, 1, and 5. Okay, those are my deviations. What I'm going to do is I'm going to square those deviations. Okay, so my values are 1, 2, 3, 4, 5, 9. My deviations from the mean are -3, -2, 1, 0, 1, 5. And so my squared deviations are 9, 4, -2 squared is 4, 1 squared, -1 squared is 1, 0 squared is 0, 1 squared is 1, and +5 squared is 25. So my squared deviations are these numbers. And then, and if I add them up, I get 40. And basically, I want to take the average. Okay. And so, again, normally, if I said take what's the average squared deviation, you would add these up and divide by 6. But for our sample variance, we're going to take this and divide by 5. Okay. And so my variance ends up being 8. And the square root of that is my standard deviation. Square root of 8 is 2.828. Okay. And, you don't ever have to do this by hand. Okay. But I think it's good to know where these numbers are coming from. And so the variance itself, I mean, when you ask R, is you say, hey, give me the variance of this number. It gives you 8. And give me the standard deviation, we get 2.828. Okay, so it's basically just taking the variance and taking the square root. Okay. And so, yeah. Do you ever have to really do this by hand? No. Is it good to know where it's coming from? Yeah. Okay. And just kind of have this picture in mind. Where's my mean? How far are each of the points? What are the deviations from the mean? And then what is the average of the squared deviations? Okay. But average is found, again, kind of in this weird wonky way where you divide by n minus 1 rather than n. Okay. All right. So that is the variance and standard deviation. Those are important. Okay. All right. Another thing that we use is the interquartile range. But before I can get to the interquartile range, I got to explain percentiles and quartiles. So percentiles, you guys are probably familiar with all of this from like standardized testing, right? I don't know. Do you guys have to take the SAT or okay? So because they made it optional, or is it not optional? I don't know. Recommended. You can't submit it. Okay. So what do you submit? Nothing? High school grades, and that's it. Okay. And what? AP scores. Okay. Do they give you percentiles for AP scores? No? Okay. You can what? You can search it? Yeah. Okay. So it's like if you get a 5, that's like, is that 90th, 95th? I don't know what percentile, what percentage of people. Huh? Depends on the class. It's 50th percentile. Getting a 5 is 50th. For some classes, everybody gets a 5. Like over half. Okay. Well, anyway. Doesn't matter. All right. Well, okay. So anyway, percentile, like if you're in the 99th percentile, that means you scored over 99% of other people, right? Like in a room of 1,000, you scored better than 990, and there might be 10 people above you, okay? In the 99th percentile, right? If you're 99.9th percentile, that means in a room of 1,000, you scored higher than 999, and maybe you're the one. Okay, but anyway, so we have, the 25th percentile, whatever. It's just whatever percentage it is, that percentage falls below that percentile, and that's that. Okay, and you can figure this out in R. You have a vector x, and you say, hey, give me the 25th quantile, 0.25, and that will give you the 25th percentile. Okay, and then so we have special names for the different quarters. 25th percentile, 50th percentile, 75th percentile. We call the 25th percentile the first quartile. The 50th percentile, I guess you could call it the second quartile, but we generally just call it the median. And then Q3, the 75th percentile, is the third quartile. Okay, it's kind of this isle, this suffix, it's like that percent is below. All right, so for the first quartile, it's like the first quarter is below, okay? And the third quartile is the 3 quarters are below the third quartile. or 75% is below the 75th percentile, right? So, you can have weirder things like quintiles and hexiles. I don't think anybody, I might have heard quintile like a couple times in my life. I don't know if I've ever heard hexile or, sometimes you hear deciles, right? Deciles would be group 10, whatever tenths, right? Like the 9th decile would be the same thing as the 90th percentile. Okay, anyway, we have that. So the interquartile range is what's the difference between the 75th percentile and the 25th percentile. And this kind of gives you an idea of like what's typical, like the 50th percentile. And then so, yeah, I think every fall UCLA is like the middle 50% of GPAs is like, all right, of applicants. I don't know. It gets crazy. I feel like it gets crazier and crazier every year. It's like the middle 50% is like a 4.2 to a 4.7 or something crazy, right? And it's like, oh, if you have a below a 4.2, you're in like the bottom 25% of that. I don't know what it actually is. I'm making stuff up, but that's what I imagine it is. I don't know. Does anybody actually know? Now I'm curious. I have to look this up. UCLA GPA. What is it? What do I look up? Requirements? No. GPA statistics? Sure. GPA stats. First year. Okay. Middle 25%. It's even worse than I thought. 4.42? What? Oh my gosh. Okay. 4.42 to 4.76. The unweighted is 3.95. Wow. Okay. You 3.94 slackers in the bottom 25th percentile. That is crazy. Okay. Well, I don't know. Maybe that's like, oh yeah. The rest of you are like, yeah, of course. I have a 4.0 and I came in with a 4.76. Of course. Okay. Well, anyway, well, you're here, so good job. Anyway, we're looking at the middle 50th percentile, right? That's and it's the range of that thing. So the spread in the middle 50 percentile. Yeah, robust to outliers. Okay, so if you got outliers, it's not affected by that. And then we determine outliers by kind of looking at that IQR. And then if you have points more than 1.5 IQRs above Q3 or below Q1, those are generally considered outliers. Okay, so with that in mind, 1.5, so an IQR for the unweighted GPA is 0.05. So 1.5 of that would be 7.075. So if your GPA is 3.875 or lower, you are an outlier on the low end at UCLA. So I don't know. I don't want to put anyone on blast here, but it's like, wow, okay. So that's how we kind of determine outliers. And then you can find the IQR and R by typing in IQR of X, okay? Most of these functions work better if you have like 100 values in your vector X. If you only have like 5 values in the vector X, it feels really weird because it's like, what's the 25th percentile of 5 values? It's a little weird. Okay, so let's take a look at an example here, and we will look at our penguins data set. I already showed you the penguins data set, right? Okay, so yeah, we like penguins. We go down to Antarctica, and so I will show you more effective methods as far as getting summary statistics from our data set, and that will be next week. But for now, let's say we wanted to just get the numbers for body mass of species Adelie, or I don't know how to pronounce it, Adelie, penguins. I think it's Adelie. And so we're going to start with our penguins data set, and then I filter just to the rows where species is equal to Adelie. Okay, and so that's going to be some of the rows. And then, but remember, the table has a bunch of columns. So if I select those rows, you know, I also have information about the flipper length and the, I forget, the beak length and stuff, okay? And right now, I'm only interested in the body mass. So I use the select function, and that just selects the column, okay? And if I stopped here, what would happen is R is going to return basically a table with one column. And if I want to be able to do like mathematical operations on it, I have to extract it out as a vector, okay? And you guys have already been kind of dealing with vectors a little bit in your data camp homework and stuff, so we're familiar with like the C notation and the vectors, right? And so if you want to get the values out of a column, you say, I'm going to pull the values, okay? So here I've been using the pipe, start with penguins, we filter it, we select it, and then we pull out those values, okay? And then at the end of all of this, the operation feels a little bit weird, but I'm going to assign it to the name Adelie mass, okay? And that's, this is going to be the vector containing the values, okay? And I do the same thing with chinstrap. I do the same thing with the Gen 2 penguins. Just filter it to that species, select the column body mass, pull out those values. And then all of them I'm assigning back to this thing, okay? And so so that's what we have. Well, I'll show you how to do this more efficiently, because you don't want to, basically I had to copy and paste the code 3 times here, or like 2 more times here, and just change it from Adelie to chinstrap to Gen 2, which is fine, but there's, you know, a more effective way where you can just say, hey, go, you know, through the species, do the same thing for all of the species, okay? And we'll look at that next week. Okay, so I'm going to take these things. I've got basically these vectors of Adelie mass, chinstrap mass, and whatever, and we can create a couple plots. We can calculate some statistics based off of these things. And so I'll show you histograms and density plots. How many answers have I given you? Just one so far? Okay, let me give you your second answer, which is the letter A. A as in apple. A as in apple. All right, so a histogram is a display for us to show how the data are distributed, okay? Same thing with a density plot. With a histogram, and if I'm going to do this in ggplot, there's only one, as far as the aesthetic mappings, you just put one value on the x, okay? And you don't assign anything to y. And I'll show you the example, okay? The x-axis is split into bins, okay? These ranges of different values. And you say like, okay, all of the penguins from this weight to this weight fit in there. And then you count how many values, how many data points fall inside that bin, okay? And then however many you have, you draw a bar with that height. That's going to be the height of each bar. And when you make a histogram, it lets you see things like the shape of your distribution. It gives you a sense of the center. It doesn't like explicitly put it. It also gives you a sense of like, are my values all spread out or not, okay? And maybe there's some skew, okay? If you use wider bins, you get less detail, but it gives you a sense of the bigger picture. If you want more detail, you can use more narrow bins, okay? Density plots are very similar to histograms. It's kind of just you draw a smooth curve instead. And it's kind of like if you drew a histogram, but then you kind of like looked at it from far away and you have blurry vision and you just draw a smooth line to kind of draw it, that's what you get a density plot, okay? Maybe it's a touch more complicated than that, but that's kind of the idea. And then the density plot is chosen, the vertical axis on the density plot is chosen in a way that if you calculate the area, like if you were to calculate the integral underneath the density curve, you would get an area equal to 1, okay? But you don't have to worry about manually calculating this yourself. But what this allows you to do is by using density plots, you can have data sets of different sizes, and they'll be relatively, the density plots will be on similar scales. Okay. Whereas with histograms, if one data set is 10 times bigger, its bars are likely going to be 10 times taller than the other one, right? Because you'll say like, how many values fit in this thing? And it might be like 5 for the smaller data set. And then for the larger data set, how many values fit in this range? It might be like 60. Okay. And so there's going to be a difference there. Okay. And you have not the bin width, but you have something called the bandwidth. And that is kind of like how much smoothing gets applied to the density plot. Okay, so anyway, let me just show you. So here, I'm taking the penguins data set. I'm filtering it to just the Adelie species. And then I'm going to do ggplot. And I'm just putting the body mass on the x-axis. Okay. So even though we went through the process of like extracting out these vectors up here, I'm not using the vectors there. I'm using still the original data set here. Okay. So I have this, and then I'm going to say do geome histogram. Bin width is 100, right? And so I think like this. I don't know the exact cutoffs, but I'm imagining it's 2,950 to 3,050. 3,050 to 3,150, 3,150 to 3,250, so on and so forth. And so each of these bins have a width of 100. And then so, how many penguins in my data set have weights between 3,450 and 3,549.9? There's like 16 penguins in that range there, okay? So the height of the bar tells you how many penguins fall within that width. And this is kind of the picture. If I were to take this and make a density curve, it looks kind of like this. And so again, it's not a perfect alignment, but it's kind of just, R does some different calculations here, but it's kind of, again, if you look at this and then you squint a little bit and you just say, hey, if I had to draw a smooth curve to kind of like connect the tips of these things, what would it look like? It might look something like this, okay? So that's the density plot. And, this still gives you a sense that like kind of the most common weight of penguin for Adelie is around 3,500 grams. And, penguins that are over 4,500 grams are pretty uncommon. Penguins under 3,000 grams, pretty uncommon, okay? And that's what we see here, okay? So I'm going to take the same data, and I'm going to just change the bin width. So now the bin width is 300, and so here's my first bar, and I don't know. This is what it looks like, okay? So it's this versus this, okay? But it's the same underlying data, all right? So this kind of gives you, again, larger bins give you kind of more big picture-ish, right? So the big picture is just like, okay, yeah, 3,500, that's around the most common. Over 4,500, less common, and I guess under 3,000 is less. But I guess there's still kind of a reasonable number there, okay? And then similarly for density, here I just changed the bandwidth. So the bandwidth and the bin width are a little bit different, but here, bandwidth here is 120, and this is kind of the smoothed out version of this.
Does bandwidth also have to do with the integrals?
No, I don't know there's some math behind this, and I don't know. I just know, this is basically a knob that you can turn, okay? And you can make this a higher knob or a smaller knob, smaller thing, and based on that, it's gonna look more like this or more like this, okay? Yeah, the bin width, that's like, if I measure the distance from here to here, it's gonna be 300. That's what this is. The bandwidth, the calculations before, I don't know, it's a little different, yeah.
Specify the bandwidth. Will it choose a size?
Yeah, there's a default that there's a formula behind its default value. You know, it looks at like the range of the values and the standard deviation of these things. There's some formula behind it, and so it has a default value. A lot of times, well, I mean, sometimes the default is fine, and then a lot of times you kind of want to mess around with it. Okay, again, the question with all of your visualizations is what is it that I'm trying to communicate, right? And then if you have something like this, you have a little bit too much detail, it's easy for your viewers to get distracted and be like, oh, why is there a little like spike here? And what does this little dip here mean? Okay. And it could be a genuinely interesting thing. And maybe that is something you want to draw attention to. Okay. It could also be as something like as simple as like when you ask somebody like, how much do you weigh? Okay. We have a tendency to just round off to the nearest 5 pounds. Okay. And it almost feels pretentious to be like, oh, I weigh 126 pounds rather than just saying like 125 or 130 or something like that, right? And so, so if you look at survey responses to like things like weight, you're gonna have spikes at like every 5 pounds, and you'll have a few like measures, like so you'll have like a whole bunch of people who say I'm 125. And then you'll have some people that say I'm 126 and 127, but then you'll have like a spike again at 130 and basically increments of 5 and stuff like that. And so if you have too many, if your bins are too narrow, then you get like kind of those weird artifacts of spikes here and there. Okay. So anyway, that's the histograms. We can do a facet wrap here, okay? And so here I say, hey, take the different species, okay, and we'll, just to make it more colorful, we'll do fill on species, and then I'm gonna do a facet wrap on species, okay? Here I specified n column equals 1, because the default is for facet wrap to make facets like horizontally, but here because I want to kind of compare the x-axis, I said make it 1 column. Okay, you can specify like the number of columns and rows. So anyway, so we get a sense of a few things, right? So the Gen 2 penguins, their average is somewhere over here. Okay, the center of their thing is over here. The Adelie and the Chinstrap are kind of down over here. And then this is where you do see a difference between the, like there were just more Adelie penguins recorded than Chinstrap penguins, and so like the tallest bar here is like 11, okay, whereas the tallest bar over here is maybe 16 or 17, okay, 18, I don't know, something else. So I can also do density, and it kind of takes this and then it does the smoothed out curves here. So I think if you kind of squint, this shape here is the same shape as the top one, which is pink or red, okay, but just kind of squished down a little bit, okay? So that's what we have here. And so by looking at this shape, we see, oh, okay, as far as spread goes, which one has more spread, Adelie or Chinstrap? Adelie, okay? So if you think about like, you can probably capture most of your values like in a smaller range here, where you're leaving off only a little bit over here and here versus over here. You kind of need a slightly wider thing, okay? And so that is reflected when we look at our standard deviations, okay? So if we look at the standard deviations of Adelie mass, it's 458 versus standard deviation for the Chinstrap, it's 384, okay? Looking at the means, okay, that's kind of like where's the center, where's the balance? Adelie and Chinstrap both have similar means, 3,700, 3,733. Like that's kind of like very similar there. Gen 2 way higher, 5,076. Okay, over here is the kind of the center. As far as the amount of spread goes, standard deviation for Gen 2 is 500. Standard deviation for Chinstrap is 384. Standard deviation for Adelie is 458. So Chinstrap has the least amount of spread, Gen 2 has the most, and Adelie would have like the second most amount, okay? And then, all right. We also have box plots. Box plots basically take your quartile information and then make a plot out of it. So the box will go from Q1 to Q3, and then there's a line inside the box for the median. You have whiskers that go from the minimum and maximum values, okay? As long as they're not outliers. And then so we draw these kind of cutoffs at 1.5 IQRs below Q1 and 1.5 IQRs above Q3. So you think of the width of the box as your IQR, and you go 1.5 box widths below and 1.5 box widths above to get those, okay? So I don't, for whatever reason, R put these in reverse order here, but it's, so Adeli, like if I flip back between this slide, okay, and this, the red is same right here, okay? And so we can see kind of this shows wider spread, okay? Looking at Q1 and Q3, we get more spread. Q1 and Q3, less spread, okay? Kind of more spread. The median is this middle line, and we can see as far as Adeli and Chinstrap, the median is like right around the same, okay? We have this dot, and this dot indicates that there are outliers for the chin-strapped penguins, okay? And so the width of the box is 1 IQR, and basically we're going 1.5 box widths down, and that's kind of the limit as far as what's not considered an outlier. 1.5 IQRs above, this is the limit as far as what's not considered an outlier, okay? If you go 1.5 IQRs up here, I think it takes you out to around here, okay? And we just don't have any points out here. So this is just the largest value in our data set. Okay, it's not an outlier, so the whisker goes to the largest value in our data set. Okay, largest value in our data set's over here, but that's considered an outlier. And so these are the quantiles, and you can kind of look and just make sure. So if you type in quantile without giving it a percentage, like 0.25, it just defaults to giving you 5 quantiles, 0, 25, 50, 75, 100. So you can see, okay, the quantile for 25% is 3350, and that's going to be this edge right here. The quantile for the 50th percent is 3700, and that's this middle line right here. And the quantile up here, 75th percentile is 4000, and that's right there, okay? Here on this slide, these are the IQRs. That's just the difference between the 75th percentile and 25th percentile. And then I did calculations for where is the boundary between outliers and non-outliers. So I did Q1 minus 1.5 IQRs for each of these things. And so we can see, like, for the chin-strapped penguins, if you figure out where the lower boundary is, 2,793.75, that's the lowest that it could be without being an outlier. And then if you look at the data, there is somebody who's at 2,700. So this would be considered an outlier. And that's what you have, okay? So, so you can kind of just double check all of these numbers, and they align with basically the plot here. All right, last view quiz answer today is the letter E. E as in elephant. E as in elephant. Okay, and that's it. Have a great weekend. And we'll see you guys Monday.